Hello everyone, this is Vijaya bhaskar. This presentation is prepared for uh, ANITS Computer Science first year students for Elements of Electrical Engineering course. Uh, I'm giving presentation and the notes is given by Appanna from Electrical Engineering Department, ANITS. So the syllabus for this unit 3 is shown in the first slide, which is DC generator principle, construction of DC generator and EMF equations and types of DC generators, efficiency and applications. Is strictly confined to these topics. The notes is given elaboratively, but from the point of view of examination, you have to adhere to only these topics, which I will go through in the next following slides. Hello, welcome to DC machines. The classification of electrical machines are divided into AC machines and DC machines. In DC machines, it is subdivided into DC generators and DC motors. The unit 3 corresponds to DC generators, which I simply call DCG. And unit 4 corresponds to DC motors. And unit 5 corresponds to AC machines, in which we will be talking about only the induction machines and transformers. You can ignore the rest of the classification, which is not there in our syllabus. So what is a DC generator? First of all, what is a generator? A generator is a machine which converts input mechanical power into electrical output power. If this generator generates a DC current, that is called a DC generator. How input mechanical power is given? So input mechanical power is given by using a prime mover. So what is it about a prime mover? A prime mover, uh, in olden days, by using a bullock or horse, you rotate so that you can uplift the water. So that is also example for prime mover. But in electrical, the prime mover is in National Thermal Power Station (NTPC), which is in your backyard. You heat the water and then you generate a steam which is similar to the one that is in a pressure cooker, and you use that steam to turn the turbine. And once you rotate the turbine, you couple the turbine into a electrical generator, DC generator or AC generator, and that is a prime mover. In case of a hydroelectric power station, you have a water at a higher height, and once the water is falling down from the higher height, you make a turbine in such a way that it has blades, and once the water falls on the blades, it rotates, and that rotated mechanical energy you couple into the generator. That's what is a prime mover there in a hydroelectric station. And once you have this prime mover, that prime mover has to cut a uniform magnetic field so that it will couple and then generate the electrical output power. So this principle is same as electromagnetic induction principle, which is shown before. So the working principle of a DC generator is uh, by using Faraday's law of electromagnetic induction. The working principle is defined here, which is defined as when a conductor cuts the uniform magnetic field, a dynamically induced EMF is produced in the conductor. The same. Let's explain further what is the EMF generated, that is induced EMF generated in this principle, that is given by E equal to BLV sin theta. So this equation was derived in the second unit in Faraday's law of Faraday's electromagnetic induction section. So I'm not going to go delve into the derivation part, but I'll give you what is B. B is magnetic flux density, and then L is the length of the conductor, V is the velocity of the conductor, theta is the angle between flux, that is uniform flux, and the conductor. So the direction of this induced EMF is given by the Fleming's right hand rule, which says that when you extend your thumb, um, index finger and middle finger in such a way that each one corresponds to one the direction of the conductor and the direction of the magnetic flux. The third one gives you the direction that the current flowing in or outward based on which way you put your three fingers. So that is the Fleming's right hand rule. So the working principle of a simple loop generator is shown here. One is the N pole and north pole and the south pole. The magnetic flux is moving from the left to the right, and there is a single loop conductor A, B, C, D, and there is a EMF collecting stuff, and then there is a load resistance. So when you rotate the single loop conductor in a uniform magnetic field, it produces electric field, which is shown here in the rightmost section, where there is a alternating current. So this specific setup gives you an alternating current, which will be in the following section. We'll be talking about how you collect this alternating current into a DC current. Another obstacle in this setup is that your collecting slip rings has to keep continuously rotate along with the loop conductor. So the typical question that can come from this slide is that explain the working principle of a DC generator. So for that you have to go through Faraday's law of electromagnetic induction, that is FEM, and then induced EMF. So don't get confused with the induced EMF of the Faraday's electromagnetic induction to the EMF generated by a DC generator. That EMF equation is different from this induced EMF. So, and then you can write Fleming's right hand rule for the direction of the current. So I'll skip the next couple of slides, and I'll jump into directly commutator. The commutator is a device which helps you to convert this alternating current to a DC current. So from previous discussion, we can clearly see that the generated output current is alternating, and to convert that alternating current into DC current or voltage, we have to use a commutator. The commutator acts as a mechanical rectifier. What is a rectifier? So it converts AC voltage or current into a DC current is called a rectifier. So the action of a commutator, how it acts as a commutator. So a commutator is a device, a cylindrical device which cut into two holes and sandwiched material is a insulating material between C1 and C2 shown in this figure, and you mount this commutator on the rotor shaft, and on the top of this shaft you connect carbon brushes which collects the current to the external load. You can see from the bottom leftmost figure how the commutator is connected to the single loop generator, and then over the top of this commutator there is a carbon brushes which collects the DC current or DC voltage to the external load. So from this slide you need to absorb what is a commutator and how the construction details of commutator, uh, and then carbon brushes, so how it is connected in a DC generator, a single loop DC generator. So I'm going to skip further details of the commutator, and I'll directly jump into the construction details of your DC generator. As you can see in the slide, as you can see here in the slide number 3, uh, the EMF generated from the output of these carbon brushes will become alternating current to DC current. So going to the construction details, so there are different systems are required for the completion of the entire construction of the entire DC generator. So which are field system and armature core, armature winding, and commutator and brushes. I'll go each and every system in the next following slides. So the typical question that can be asked from the construction details of DC generators is what are the different systems present, and explain these construction details of DC generator. So going to the details of construction details of a DC generator, the first thing is field system. As you can see here, uh, I refer everything to this every construction details to this figure, where you have a magnetic flux path which is called a yoke, which is a metallic structure. uh, uh, there are poles embedded on this metallic structure, which generates the magnetic flux, and then that passes through the yoke, and it will, as you can see here, there is an arrow symbol, dotted arrow lines that closes the magnetic flux path. And here there are total 4 poles, that is north south. But if you look at in a simple loop generator, there are only 2 poles. So remember this thing, which is useful in the EMF equation derivation of for DC generator. So here these poles are excited and generated a constant magnetic flux by using coils, that is called field coils. So this is the beauty of 20th century electrical engineering. You can generate a magnetic flux by exciting with the electric current, rather than in a simple generator you just put 2 magnets. But here, as you go and do engineering of bigger and bigger generators, it is not possible to place which can generate a high flux magnets. So you generate the magnetic field by giving excitation to the field coils. That's why you have 4 field coils, and if you put more than 4 and then further and further, the design will be different. So essentially you can see these poles are in a parabolic shape, um, uh, looking towards the armature structure. This is the top view of the DC generator. So the second one is armature core. This is a solid structure which is sawtoothed, and there are small circular things which are the your windings. That is, if you look at in a simple generator, there are only one loop of winding, but to accommodate as many as loops, so you use the armature core, which is a this is fixed to shaft and rotates between the poles, uh, and it consists of a soft laminated iron core material or cylindrical core material. uh, so if you ever opened and looked at the fan, there are all these copper wires were connected from one end to the another end in a different shapes, like a French braid of a herring. So there are different types of constructions. Based on that, your um, the armature parallel paths, they are called. They will differ, and you will use that armature parallel paths for EMF equation of a DC generator. So in summary, uh, the construction details of DC generator consists of a field system where you have number of poles are connected, and the field flux path has a closed loop path. And the next one is a armature core, which is a fixed shaft and rotates between the poles. And the armature windings is copper wires connected either in a parallel or series manner. And the next one is commutator, which is also called a mechanical rectifier. You can give the definition of the rectifier. And then brushes. So this completes the construction details of a DC generator. I'm going to skip armature windings in this slide number 4, which is marked as a 4. And then I will skip the next page, and then I'll directly jump into the page number labeled as 5, where there is a EMF equation of a DC generator. So the armature winding. So in the armature winding, the slots in the slots we connect uh, copper wires which are insulated from each other, which are called armature winding. In which the armature winding is connected in different ways to uh, increase the current. If you want to increase the current, or if you want to increase the voltage, you use different methods. That we will use for when we go into the EMF equation. You will use that how these armature windings are connected. And the next one is commutator. As we already discussed that it is also called a mechanical rectifier, which converts generated AC current into a DC current or DC voltage. So it is made of copper segments sandwiched, insulated by mica sheets, and mounted on the shaft. And the next one is brushes. Brushes are the one you keep on the top of the commutator, which is similar to the one the brushes we use in the railway electric systems. So these are made of carbon and rest on the commutator. So the EMF equation of DC generator. There are different parameters you need to understand before we jump into the derivation of the equation. The phi is the magnetic flux per pole. There are, if you remember in our figure, there are a number of 4 poles are there. So that is the one corresponds to the magnetic flux here. And Z is the total number of armature conductors. P is the number of poles. A is the number of armature parallel paths. You can ignore if it is a wave winding or lap winding for the time being, but it's just the number of armature parallel paths. N is the speed of the armature rotation, which is given in rotations per minute. And Eg is the EMF of a generator, EMF, which is equal to EMF per parallel path. So if you remember from the Faraday's law of electromagnetic induction, the general equation is EMF generated in one conductor is N d phi by dt. So N, if you assume N is for one conductor, that will become d phi by dt. We will find d phi separately and dt separately from here, and then we'll find the EMF equation for a single conductor in d phi by dt. D phi equal to the number of poles P multiplied by the flux per pole, magnetic flux per pole, that is pi. So phi, that is P phi. And the time taken for one revolution that is dt equal to 60 seconds 60 by n here, that is dt. And how did you get d5 by dt? Here our speed is given in revolutions per minute. You just divide that number of poles, 60 convert into seconds, so it will become 60 by n. And from here, from the from the d5 and dt, we can find the EMF equation d5 by dt equal to p5 by 60 by n. That will become 5 p n by 60 volts. Remember, here this is only for one conductor. So here there are different number of parallel paths. So you have to find how many conductors are there in different number of parallel paths. That will become Z by A, which will give you number of conductors in a parallel path. So you have to multiply that Z by A into the EMF equation for one conductor, that is 5 P N by 60, and the final equation become 5 Z N P by 60 A volts. So from here you can see here uh, for any electrical DC generator, the number of poles and the Z, that is total number of armature conductors are, once you design, they will become constant. But the by varying the n, that is the speed of the armature, and by varying the excitation, you can increase the field generated by a DC generator. So simply Eg is directly proportional to phi n. So this is the most important equation from this chapter. So you need to understand and by heart the EMF equation of a DC generator. So one another additional concept that we were missed before is armature resistance. So this is the resistance offered by the armature circuit, which is equal to Ra, and this is generally of 1 ohms. So the next concept is types of DC generator. Based on the method of excitation, DC generators are classified into separately excited DC generator or self-excited DC generator. That means if you remember, those field poles are whether you are giving the excitation separately, or you are taking the generated EMF and then you are exciting. You are connecting and then exciting. Based on that, you are subdivided into two types. So the separately excited DC generator, where the field windings are supplied from an independent external DC source like a battery, is called separately excited generator. So the generator symbol is a circle, as is shown here, easy. Over that there is a brushes, and then load is connected, where there is a load current of IL is applied and a voltage of V, and this generator has the armature resistance of Ra, and the field we have kept outside. So field coil is generating a flux of phi with which is excited by a battery here, and a current, the field current is shown here, I IF, and here the generated EMF Eg is proportional to phi n. So from here you can find the equations for shown here. The armature current equal to load current plus shunt current, and the terminal voltage is generated EMF minus armature voltage drop, that is IaRa, and the power delivered is Eg Ia, and power delivered to the load will become V into IL. So the second one within the uh, self-excited DC generators is DC series generator, in which you place your field coil in series with the DC generator shown in this picture, and the resistance will be smaller, so that the entire current will be passed to the load of the generator. And similarly, the one that we find equations, we can find armature current will be equal to the shunt current equal to the load current, and we will find the terminal voltage by subtracting armature voltage drop, that is IARA, and shunt voltage drop, that will become your terminal voltage. Uh, Similar to the one that we find previously, power developed and power delivered to the load in the equations. We'll use these equations in problem solving, so please try to understand how these equations are derived. These are simply how you connect the circuit and then place your resistances, apply KVL and KCL so that you can find the voltages and the current, and then the power delivered, power absorbed, all those things are there in the circuit diagrams. So the last one is DC compound generators. Here you use both series and shunt field resistances. And within this DC compound generators, there are two types. One is a short shunt and another one is a long shunt compound generator. If you look in this next slide, in the short shunt generator, uh, you will place the series field coil at the output in series with the load resistance, and in long shunt you place your series coil in series with the uh, electric generating thing. And there are two different equations based on like how you connect the circuit. You can find uh, uh, I series equal to I load here, and then by applying KCL to the short shunt generator, you can find armature current equal to IL plus I shunt, and the voltage at the terminal equal to EG minus IARA minus I series and R series. Similarly, you can find I shunt equal to EG minus IARA divided by R shunt. There are similar equations for power delivered, power developed for these two different types of generators. Uh, I'm going to skip losses in DC generators and then a couple of more things, and directly jump into the power stages so that we can find the efficiency of the DC generator. So uh, the slide number is after 8. There is a power stages of DC generator that gives you the last topic, the efficiency of DC generator. So there are three different stages. So one is a mechanical input power and electrical power developed at the armature, and electric power connected to the load. From the point that is electric from the coal boiling to the entire power delivered, the efficiency will be of the order of 30%. But if you take from the electrical power developed at the armature to the electrical power given at the output, there will be around 97% efficiency. That's why you need to that's the beauty of the electrical engineering. So in between mechanical and electrical power, there is iron and friction losses within the how you connect the shaft to the mechanical prime mover to the shaft. There is iron friction losses. In between electrical power developed in the armature to the connected to the load, there is a copper losses. So how you define the efficiency is generally defined as output power by the input power. So so this is a function of both mechanical efficiency and electrical efficiency. At the mechanical section, that is mechanical input power to the electrical power output at the armature, uh, that is one efficiency. That's called mechanical efficiency. That is easy IA divided by mechanical input. The second one is electrical power developed in the armature to the electrical power developed to the output. There the efficiency will become VIL, that is output at the load, that is power at the load, divided by the power generated at the armature, e.g. IA. and the total overall efficiency will become multiplying both this mechanical efficiency and electrical efficiency, the VIL divided by mechanical input, that is NE and NM. So the rest of the topics are not relevant to your syllabus, so I'm directly skipping to the last section, which is applications of DC generator. There are different applications, you can just read and understand yourself. So I'm going to skip the topic, and that gives the end of this topic. So essentially what we covered today is that the classification of electrical machines, DC and AC, and DC generators, and then DC motors. So this unit is confined to DC generators, in which first we spoke about the operating principle of a single loop generator, and then how it generates the EMF, and we talked about the commutator, how there are different construction details of a DC generator, where we spoke about the field system, armature core, armature winding, commutator, and brushes, and the design details of them. And then next we talk about the EMF equation of a DC generator, where you find the equation is equal to phi z and p by 60A. And also you find EZ is proportional to the flux and N. The and the next topic, we spoke about different types of DC generators, where there is a separately excited and self-excited DC generators. In self-excited DC generator, there are three different types of generators: DC shunt generator, DC series generator, DC compound generator. So the most important thing from this is EMF equation of a DC generator, and then the simplified diagrams of DC shunt generator, DC series, DC compound generators, and then voltage equations and power equations. So if you can understand, you can solve the problems. And finally, the applications, the efficiency of a DC generator. And the last topic is different applications, which you can read on your own. That's the end of this unit 3 theory. I'll be going to discuss a couple of tutorial problems for the next session.